Hi, and welcome to this lesson on sensitivity. Sensitivity is the minimum power that must be applied to the input of a system that is required to achieve a specified quality of output. That definition is pretty vague and can be interpreted in a number of different ways. In this lesson, I'll walk you through the various concepts that are collectively sensitivity and the associated definitions. First, we'll talk about the sensitivity of receivers. For this, the concept of MDS, that is, minimum detectable signal, is useful. Then we'll talk about the sensitivity of receiving stations, that is, combinations of antennas and receivers. First, I'll show you how to compute pre-detection signal-to-noise ratio, which is a metric of output quality, and we'll do that given parameters that we've defined in previous lessons. Then we'll define the concept of system temperature, which is one way to quantify the overall noisiness of the receiving station. And then we'll define the concept of intrinsic sensitivity, which can be expressed in a number of different ways, including AE over T cis or G over T. Before we get started, just fair notice that I'll assume that you already know about the concepts of equivalent noise temperature, noise figure, antenna temperature, and antenna gain. These are all things that were introduced in previous lectures. First, let's consider the sensitivity of a receiver. And by this I mean just the receiver, not the antenna or anything else. Specifically, the question is, what is the minimum power that I can apply to the input of a receiver that results in a specified quality of output? Now, as stated, that question is pretty vague. To clarify the question, we need to add some additional detail. The yellow box on this slide represents the receiver. For the purposes of this lesson, it's useful and sufficient to think of the receiver as consisting of just two things: a front end and a detector. The front end applies gain, G, and sets the bandwidth, B, and also contributes some internal noise. The internal noise will represent as the input referred equivalent noise temperature, T sub R. Now for the detector, we want to account for all the possibilities. So here the detector could be an analog to digital converter and everything following that, or it could be merely an analog envelope detector, or any of the myriad other possibilities. We don't want this analysis to become overly specific or unnecessarily complicated, so here's what we're going to do. We're going to limit our interest to the input of the detector. Specifically, we're going to address the signal-to-noise ratio at the input of the detector. We call this the pre-detection signal-to-noise ratio. Now this does a trick because once we know the pre-detection signal-to-noise ratio, we can figure out the performance of the detector, whatever the detector may be, and we can do that as a separate step. Okay, we're ready to define receiver sensitivity. The specific metric of receiver sensitivity that we'll consider first is minimum detectable signal, and that's abbreviated MDS. Now, as we'll see shortly, there are actually multiple definitions of MDS, so let me now clarify that what we're going to address first is the zero input noise definition of MDS, which is illustrated on the slide now in front of you. In the zero input noise definition of MDS, we consider a scenario in which the desired signal is delivered to the receiver with a power P sub R, and there is no associated noise with the signal. In this case, all the noise that arrives at the input of the detector originates from the receiver itself. And to a good approximation, this is what you might expect to see in a lab measurement. Calculating the pre-detection signal-to-noise ratio is simple in this case. First, we calculate the signal power, S, and this is just P sub R times the gain of the receiver, G. The associated noise is K, which is Boltzmann's constant, times T sub R, and then times the bandwidth, B, and that gives us units of power. And then we multiply by G, because T sub R is referred to the input. So pre-detection signal-to-noise ratio is just P sub R divided by K times T sub R times B. Note that the receiver gain, G, has canceled out, and this is expected since the gain of the receiver is affecting both the signal and the noise in the same way. Okay, now we're ready to define MDS. The equation in the upper right of this slide is simply the equation we just derived, but now we write S to N as the Greek letter rho, and P sub r is replaced with MDS. In other words, we're defining MDS as the power, P sub r, which results in a specified pre-detection signal-to-noise ratio, which we're calling rho. Now, this is important. MDS cannot be defined independently of rho. Sometimes the presumption is that rho is equal to 1, in which case MDS is the input power that gives you pre-detection signal-to-noise ratio equal to 1. But you'll also see cases where rho might be specified to be equal to 2, or to 3 dB, which is pretty close to 2, but not exactly the same value. Or 10, which would represent a much higher standard for detection. Any of these is fine. The important thing is that everyone knows the value of rho that defines MDS. Now, with that understood, we solve this equation for MDS, and that gives us rho times K times T sub r times B. And that's really all there is to it. MDS is how many times the pre-detection noise power, referred to the input, that you consider necessary for acceptable performance. Now, sometimes it's more convenient to work in terms of noise figure than noise temperature. For example, you might not know T sub r, but you might know the corresponding noise figure, F sub r, for a specified reference temperature, T sub naught. And in that case, you can simply say that MDS equals rho times K times T sub naught times F sub r minus 1 times B. Now, of course, F sub r in this equation is in linear units. That is, its noise factor and not something in dB. Also, make sure that you have the right value of T naught. Now, almost always F sub r is defined with respect to T naught equals 290 Kelvin. That's the IEEE standard definition. However, from time to time, someone will have a different value of T naught in mind, and then the associated value of F sub r will be different. And if you don't account for that, then your value of MDS will be incorrect by some amount. As we proceed in this lesson, we'll stick with the definition that T naught equals 290K, and we'll assume F sub r has been properly determined with respect to that value of T naught. Finally, before moving on, note once again that this is the zero input noise definition of MDS. So now let's consider another possible definition of MDS. In the non-zero input noise definition of MDS, we account for the noise arriving at the input of the receiver from outside the receiver. In the picture shown here, that noise is expressed as the quantity K times T sub in, which gives us the noise power spectral density arriving at the input. This extra noise is obviously going to decrease the pre-detection signal-to-noise ratio, so we're going to get a worse, that is a higher, value of MDS. And you might feel that this definition is unfair to the receiver, since the receiver is not responsible for that extra noise, and you would be right. Nevertheless, sometimes this particular value of MDS is closer to what you actually want or need to know. Sometimes what's most important is the MDS considering both the receiver and the external noise, because that's the sensitivity of the receiver as it might actually be used. So let's continue. Here we're following the same procedure as before to calculate the pre-detection signal-to-noise ratio. The expression for S does not change. The expression for N changes only in that the equivalent noise temperature is now T sub in plus T sub r. So we get the new expression for S to N shown here. And the outcome is not surprising. MDS for non-zero input noise is the same as that for zero input noise, with the only difference being that T sub r increases to T sub in plus T sub r. And, as before, we can write this expression in terms of the noise figure of the receiver, as opposed to T sub r. Here I'm simply expanding the expression and making the substitution for T sub r. In the final line, I've regrouped terms, and I've done that to make a point. The second term inside the square parentheses captures the effect of the internal noise of the receiver. The first term captures the effect of the input noise, but what's interesting is that it's proportional to input noise temperature minus the reference temperature for F sub r. On the next slide, I'm going to show you why that's interesting. Let's say I arbitrarily choose T sub n to be equal to T naught. In this case, the expression for MDS, according to the non-zero input noise definition, simplifies to the expression that I've shown in the box here. We find that MDS in this case equals rho times k T naught B times F sub r. Now if T naught is 290K, then k T naught, the product of those two factors, is about 4 times 10 to the minus 21 watts per hertz, which is about minus 174 dBm per hertz. If you work around RF engineers long enough, you will see this number, minus 174 dBm per hertz, show up everywhere, and this is why. Simply put, minus 174 dBm per hertz is the minimum possible value of the non-zero input noise MDS, when the input noise temperature is equal to the IEEE standard reference temperature of 290K. Let me say that again. Minus 174 dBm per hertz is the minimum possible value of the non-zero input noise MDS, when the input noise temperature is equal to the IEEE standard reference temperature of 290K. Now, this turns out to be useful for simplifying calculations. We get a simpler expression. But this little quirk also creates a lot of confusion. So let me be clear. If the input noise temperature is not equal to 290K, then the minimum possible value of the non-zero input noise MDS is different, because KT naught will be different. The problem occurs when folks treat this number, minus 174 dBm per hertz, like a physical constant. It is not. It is merely an arbitrary but widely used reference value. In particular, nothing special happens at minus 174 dBm per hertz. It's just Boltzmann's constant times an arbitrary value, and the arbitrary value is 290K, and that's it. So, something to keep in mind. Okay, on to the next topic. Now we want to consider the sensitivity of the complete receiving station, that is, antenna plus receiver. To do this, we'll keep the receiver model we previously developed, but we'll add a model for the antenna. As shown on this slide, the antenna is represented by its effective aperture, A sub e, and its efficiency, epsilon. Here, epsilon accounts for everything that causes the power delivered to the receiver to be less than what would be implied by A sub e. For example, it can account for impedance mismatch that causes reflection. It can account for polarization mismatch, and so on. Epsilon can also certainly account for loss within the antenna, but just keep in mind that if you have significant loss due to resistance within the antenna, that itself will create some noise, and you'd have to separately account for that. To keep it simple here, we're assuming no such additional noise from ohmic losses within the antenna. The signal input to the system is S sub r, as shown on the left. This is a spatial power density, that is, watts per meter squared. The noise input to the system is the spectral power density, K times T sub A, where T sub A is the antenna temperature. Now, if that term is unfamiliar to you, no worries. It was introduced in another lecture, so if necessary, go back and get that info. For now, it suffices to know that the antenna temperature, T sub A, represents noise received by the antenna from its environment. Now, as before, we want an expression for the pre-detection signal-to-noise ratio. It's easiest to work that out in two steps. The first step is to see what we have at the interface between the antenna and the receiver. Here, signal power, S, is just S sub r times A sub e, as usual, and this will be reduced by the efficiency, epsilon. The noise power is just K times T sub A times B. Now, we haven't actually band limited the noise through the receiver yet. We're just anticipating that this is going to happen later. There's no harm in computing the noise power N now by anticipating the band limiting by B later. And again, this power is multiplied by epsilon since it all passes through the antenna. So, the signal-noise ratio at this interface is given by the expression shown at the bottom here. Note that the result does not depend on epsilon, which is canceled out. All that means is that the signal and the noise are both affected by epsilon in the same way, and so we should not be surprised to see that the signal-noise ratio at this interface does not depend on epsilon. And here's what's happening at the input of the detector. S is increased by the receiver gain, G, as expected. N gets an additional term representing the internal noise of the receiver, and then the sum of those two noise terms goes up by a factor G by passing through the receiver. So, for pre-detection signal-noise ratio, we get the expression now shown in the lower right. Note what's happened here. The receiver gain, G, cancels, and it cancels for the same reason it cancels for MDS. However, the efficiency, epsilon, no longer cancels. The reason this expression depends on epsilon is simply because the noise injected by the receiver is independent of the efficiency of the antenna, because it doesn't pass through the antenna. So, pre-detection signal-noise ratio does depend on epsilon. Here I've rewritten this expression simply by dividing the numerator and the denominator by epsilon. So now epsilon is completely contained in one place in the expression. The resulting factor of t sub a plus t sub r divided by epsilon, now appearing in the denominator, has special relevance. So let's call that out. We call this factor the system temperature. The reason for giving this a name is because this factor now accounts for all relevant noise contributions. It is literally a measurement of the overall noisiness of the system. We'll call the system temperature T-sys. If we now substitute T-sys into our expression for the pre-detection signal-noise ratio, we obtain the new expression shown on the right. And this is what we were after. This is the pre-detection signal-noise ratio for this system, neatly expressed as a function of effective aperture, system temperature, the instant power density of the signal, and the bandwidth of the receiver. The factor of AE over T-sys stands out in this expression for the following reason. This factor captures everything relevant about the design of the receiving station that determines sensitivity. Now, you might say that the bandwidth, B, is also part of the design of the station. But what's actually happening in this expression is that B is there simply to convert the power density, S sub r, that is so many watts per meter squared, into a power flux density, that is so many watts per meter squared per hertz. AE over T-sys, on the other hand, is completely independent of the signal S sub r. AE says how effective the antenna is in scooping power out of the radio wave, and T-sys describes the overall noisiness of the system. This makes AE over T-sys a convenient way to describe the overall sensitivity of the receiving station. It is the intrinsic sensitivity of the station. It's something that you could specify to a designer and have confidence that the resulting design meets your sensitivity requirement. Further, you need to determine AE over T-sys only once, and then it's easy to get the pre-detection signal-noise ratio for whatever specific situation you may encounter, and you would do that using the equation shown here. Now, I have to warn you about one other potential pitfall, which once again pertains to definitions. Here, as in previous lessons, we've defined S sub r as the power density in one polarization. However, in astronomy, we tend to define power density as being total power density, that is, the total power incident in both possible orthogonal polarizations. Typically, the power in an astronomical signal is evenly divided between these polarizations. So if you look up this equation in an astronomy textbook, you'll probably see an additional factor of 1/2, with that factor of 1/2 accounting for the fraction of total power that you can extract from just one polarization of the antenna. Now, there's no paradox or inconsistency here. This is merely a matter of definitions, and something to keep in mind. Here's another way to describe the intrinsic sensitivity of a receiving station. We begin with the previous expression, but then we eliminate the effective aperture by substituting the formula for directivity in terms of effective aperture. That formula is directivity is equal to effective aperture times 4 pi divided by wavelength squared. After the substitution, we obtain the expression on the right, which is now in terms of directivity as opposed to effective aperture. Now, in lieu of AE over T cis, we have D over T cis, that is directivity over system temperature. This too is an intrinsic measure of the sensitivity of the system, and this may be more convenient if you're working in quantities expressed in terms of directivity as opposed to effective aperture. Now, you'll often see this quantity referred to as G over T, which is shorthand for antenna gain over system temperature. And that's more or less true if the efficiency of the antenna can be neglected. If the efficiency of the antenna cannot be neglected, then obviously D over T cis is not quite G over T cis. So calling this quantity G over T might lead to confusion. Again, definitions are important, so just be careful when someone hands you a number that's stated to be the G over T. Okay, let's wrap up with a review. First, we talked about MDS, which is the power that must be applied to the input of a receiver in order to achieve a specified pre-detection signal-to-noise ratio. We obtained two definitions of MDS. One is based on zero input noise. The other accounts for the possibility of non-zero input noise, in which the input noise temperature is often, but not always, assumed to be equal to the IEEE reference temperature of 290 K. And I alerted you to the possible confusion about the associated factor KT0, which in this case would be equal to minus 174 dBm per hertz, which, once again, is merely an arbitrary reference value and not a physical constant of nature. We worked out an expression that lets us calculate the pre-detection signal-noise ratio for an entire station, including an antenna and a receiver. And I warned you about the 1/2 flux issue. That is, just be careful that you know whether the input signal power is being defined in terms of a single polarization or all the power available in two orthogonal polarizations. Along the way, we defined system temperature, T cis, which you can think of as the overall noisiness of the system, accounting for contributions from both internal and external noise. Finally, we've defined the intrinsic sensitivity of a receiving station, and we've done that in terms of the metrics AE over T cis, having units of meters squared over Kelvin, and G over T, having units of 1 over Kelvin, or dB per Kelvin. Here I pointed out a common source of confusion having to do with the efficiency when using the metric of G over T. Again, definitions matter. That concludes this lesson on sensitivity. Thanks for listening.